Okay, this section is about forces between current carrying wires. So we're going to look at the magnetic field around a wire that's carrying electrical current, and we're going to try and look at the forces between two wires that are both doing that, and we're going to look at how to use that to define the value of the ampere. So here's the magnetic field around a single wire. You'll notice that the little dot in the middle here tells you that the current is coming towards us in this diagram. There's some important points to notice here. First of all, the wire in this, the magnetic field in this case is going anti-clockwise, and you need to be able to find the direction of the field around a wire. So one way to do that is with the right hand grip rule. So here's the grip rule. You point your thumb in the direction that the current's going, and then your fingers will wrap around the wire in the same direction that the field's moving. There is another rule called a screw rule, where imagine if this, it's easier to see if this wire was going away from you, you'd see the crosshead of the top of the screw, and then as you tighten the screw to make it go away from you, then the field would be going clockwise. Okay, but it's a little bit more difficult when it's coming towards you, so it may be a bit easier to use this right hand grip rule. Obviously, like with a left hand rule, it's very important that we remember to use which hand to use. Okay, so call it the right hand grip rule, not just the grip rule, and that'll remind you of which one to use. It's symmetrical around the wire, as you might imagine. There's no reason why the field would be different over here to what it is over here. So we get concentric circles, so at the same distance from the wire, the flux density is the same, and the flux density is lower as you get away from the wire, as you would imagine. Otherwise, obviously, you know, a wire could be a million miles away and the flux density would be the same. So the way you can see that from the diagram is the fact that the lines are getting further apart. If you remember with a bar magnet, when you saw all those lines close together, that told you the flux density was strongest at the poles. Well, in this case, the flux density is strongest closest to the wire. This is actually an inverse relationship. So if you're twice as far away from the wire, the flux density is half as much. Okay, and that's the grip rule that I've said. So if we've got two wires and we want to work out the force between them, the easy way for us to think about this is to imagine that one wire is creating the magnetic field, and then the other wire is a wire inside that magnetic field carrying a current. So if we look at this wire here, this wire is creating the magnetic field we've just shown. Think about this wire. You might want to just pause the video here and try to use the left hand rule to work out the direction of the force. So if you do that, you've got your second finger pointing towards you, you've got your first finger for the field pointing upwards, and that should give you a force to the left here, so it's going to move towards the other wire. So the force on this wire is towards the other wire. If we then reverse that process and we say, well, let's have a look at the force on the other wire. This wire is now in the field of this wire. So, and if you do that, you'll get a force. If you do the same thing, the current's still coming towards you, but now the field is coming this way. So your first finger is pointing in the opposite direction, so it makes the force go in the opposite direction. Okay, really, if you got the first one, Newton would have known about this second one, because he would have known that if body A exerts a force on body B, then body B exerts a force of the same magnitude in the opposite direction on body A. Okay, so the forces must be in opposite directions. So this is two wires carrying a current in the same direction, and they will attract each other. If you repeat the process for one wire being reversed, you'll find that they repel. So this is kind of the one exception that I can think of in the whole of physics to the rule of opposites attract. This is the rule of in the same direction they attract. If they go in opposite directions, they repel. Okay, and we can use this effect to define the ampere. Okay, and we can demonstrate it. So I'm going to put in a little video here to demonstrate how that's done in practice. It is a very small force, so it's quite hard to actually demonstrate the effect in reality, but hopefully you'll be able to see on the video. Okay, this is the demonstration of the force between two wires. So we've got two long aluminium strips here. They're both connected at the moment to the positive at the top and the negative at the bottom, so the current's going the same way down both wires. So if we think about this wire, the current's going in this direction, so if we use the right hand grip rule, I put my thumb in the direction of the current, the field is going that way around the wire. That means this wire is carrying a current down and the field is going towards you. So if I take my left hand That means the field is going that way, the current's going down, which gives my thumb pointing in that direction, so the force is to the left. Okay, we could do the same thing for this wire, so again if I use my right hand, the field's going this way, so in this one the field's coming towards me. If I use a left hand, the first thing, the field's coming towards me, the current's coming down, that means my thumb's pointing that way. So this is providing equal and opposite forces to make the wires attract. So if I turn the electricity on, the two wires will move together. Turn it off, then they go back. Okay, if that was a bit hard to see, just a bit in closer. So if you look at the wire here, that's the current on, turn the current off, turn the current on, turn the current off. Hopefully you can see those two wires are attracted to each other. This is an important idea because this is used in the definition of the ampere, which we're going to do next. So this effect is used to define the value of the ampere. If you remember back to year 12, we talked about the ampere, but somehow, like all the other quantities, the units that we have in physics, we have to define it. So remember, we have to define the kilogram, the metre and the second. These are absolutely fundamental units. They get defined in slightly different ways now. So the second is defined as the number of vibrations of a certain kind of atom. The metre is the distance that light travels in that time in a vacuum. The kilogram, they're working hard on trying to change this, but the kilogram is still defined according to a standard kept in Paris, like what they call a prototype kilogram. But once we've got these three, we can define the Newton. So the Newton is just a force of 1 Newton causes a mass of 1 kilogram to accelerate at 1 metre per second squared. Look at the units we've got there. The kilogram we've defined, the metre we've defined, the second we've defined. We've now got a Newton. And if we just have those things, we can define the ampere to do with the force between two wires. So a current of 1 amp in each of two infinitely long wires. Okay, obviously you might be thinking, hang on, where are you getting these infinitely long wires from? But this is the definition. Placed 1 metre apart in a vacuum causes a force of 2 times 10 to the 7 newtons per metre. So it's a very small force, right? But it's exactly 2 times 10 to the minus 7 newtons per metre. Okay, so that allows us to define the ampere. Once we define the ampere, okay, then we can do lots of other units. So you might think at the start of this, hang on, I know an ampere is 1 coulomb per second, but that's not correct. A coulomb is in fact the amount of charge you get when a current of 1 amp flows for 1 second. A volt is 1 joule per second. If you're thinking, hang on, you haven't defined the joule. A joule is 1 Newton times 1 metre, so we can define the joule. 1 joule per coulomb is 1 volt. 1 volt per amp is 1 ohm. And the Tesla is the most important one for this unit. That you notice that we defined, we had to use the amp because it was we said that the flux density was 1 Tesla. Okay, if there were a wire carrying 1 amp, felt a force of 1 Newton per metre. Okay, so hopefully you can see from this in the SI system how we have to build our units and be careful how we define them. Okay, so 3 questions. The definition of the ampere. What's it tell you about the flux density 1 metre from wire? Well, we know the equation, F equals BIL, and we've defined for the ampere that this force is 2 times 10 to the minus 7 newtons. The flux density must be B times the current of 1 amp times the length of 1 metre, because it's this force per metre. So the flux density is 2 times 10 to the minus 7 Teslas. That's a very weak field. Okay, so that's why the force is so hard to demonstrate. Okay, what would happen if the current was 2 amps? Well, the flux density would be doubled because the wire that's creating the force, the field, has got twice the current, so you get twice the flux density. But the wire that's feeling the force has got twice the current, so I is doubling as well. By the time you've doubled both of those, twice the flux density, twice the current, that will give you 4 times the force. So now we get 8 times 10 to the minus 7 newtons. So putting a bigger current through both wires makes the force a lot easier for us to see. Okay, and hopefully you've seen from just what I said before, the ampere needs to be defined before the Tesla, because the definition of the Tesla is the flux density when a wire is carrying a current of 1 amp. You couldn't write this definition for the Tesla until you knew how much 1 amp was. Okay, 1 Newton per meter is the force. So once we define the amp, the Newton, the meter, then we can define the Tesla.